record. Okay. All right. So I'm going to share my screen.
Okay.
And here is my Chrome window. All right. Okay. So I'm about to present this research that I've done for the last few years. And it was really originally motivated by a problem I had inside of Google. And I will not get into details of what that was because it's, Google business. But essentially, yeah, let me just step through the slides and hopefully it's self-explanatory.
Okay.
So this talk is about homogeneity tests. So they are two sample tests of distributional equality, and two sample tests means that you have as inputs both x and y, and we can formulate it as x has its own distribution, right? An IID sample of distribution P, y is IID of the distribution Q, and then the question that we're asking is P equal to Q? Are they the same distribution or not? Right? So it's a very general question, and let me step to the next slide, and then yeah. So if you're familiar with the stuff, you may have heard of Kolmogorov-Smirnov test and so on. But let's talk about one sample tests also. So if either of the distributions is known, without loss of generality, assume P is known, then you're only testing whether the samples you observe of Q match the distribution P. Right, and the usual statistics also apply. The same statistics like Kolmogorov-Smirnov can be used in one sample or two sample settings. But the theory, if you read up the theory of the stuff, we're trying to look for powerful tests and so on. In a simple versus simple scenario, meaning if you're hypothesizing that either X follows distribution P or distribution Q, and both of those are known, then the power of the test is a function. I'm hand waving a little bit, but it is essentially a function of the KL divergence between the two distributions. And what this means in particular is because the KL is an asymmetric divergence, that if you were to flip this around and your null hypothesis is now the second distribution and your alternative hypothesis is the first distribution, you may have a different p-value. You may now become a lot less confident or a lot more confident, or in terms of, let's say controlling for sample size. Let's say you given 10 random samples, right? You may have a much stronger p-value in one direction or the other. Or to say it differently, let's just say the average sample size required to reject the null may be a lot larger in one setting or the other. All right, so I just said the same thing in different ways. And the reason for this is because the KL divergence is reflecting a reality, an information theoretic reality, right? That the evidence is in fact stronger in one direction than in the other. Right, this is what I have highlighted here in the red. So just as a concrete example, we can let P1 be the normal distribution 0, 0, 1, so variance 1, and P2 is normal 0, 2, meaning variance is equal to 2. This is an example in which the KL divergence will change once you flip the two distributions. And in particular, the KL divergence from P1 to P2, so from the thinner to the wider distribution, is 0.31, 0.32, And in the opposite direction, KL divergence from P2 to P1 is a lot bigger. It's 0.804. And as a consequence, it's a lot easier to reject P1 when P2 is true than vice versa. Is this intuitive? Why would this be true in this direction? Yep. I don't think it's intuitive for everybody. And I want to spend a minute giving a little intuition of why this is true. So when P1 is true, the real distribution is fairly narrow. And you're considering the hypothesis that it's narrow or wide. And every time you observe a point really close to the middle, because that's what you're going to get, you're going to get stuff near the middle, this is only weak evidence against the wide distribution. But now let's flip it around. And the wide distribution is the true one. Very quickly, you're going to end up with a point really far away from the middle. And that becomes very strong evidence against the null. So if P2 is true and P1 is your null, then you will very quickly reject that. So I think that's a good intuition. And then the next, so what we should think about now is, let's go back to the classic stuff. So Kolmogorov-Smirnov, right? It's just this supremum of the differences of the empirical distributions. And clearly, if two distributions are different, it will have a positive value for that. And as the sample size gets bigger and bigger, the null distribution of the statistic, converges to 0, right? Which means that as the true value of the statistic will converge to a constant, whereas the null distribution will converge to a distribution around 0, and so you become increasingly confident that the null is false, and you reject with more and more confidence. I just need a second. I'll be right back. All right. So two sample homogeneity tests. Right. So that's what we're discussing now. Permutation tests. So what you may learn in stats class is that there's some asymptotically normal distribution for the statistic, as with almost every statistic. And once you have a large enough sample, you say, well, this approximation, you can approximate your distribution using the asymptotic distribution. But we live in the era of computers, and my belief is that statistics education is still living in the 80s. And we really should be using resampling methods to get an exact distribution, or as close to exact as you can. And so, methods like bootstrap and permutation tests, right? So a permutation test is a simple idea in which, for two sample testing in particular, when you have two samples, you merge them to get a combined sample, and then you randomly draw some number of them to be on the first sample and some number to be in the second sample, and these numbers have to match the sample sizes, right? So if we have 7 and 3, then we take resamples that have that, or let's say partitions. Then we take partitions of the combined sample that have 7 on one and 3 on the other, right? So to note about this, and the KS statistic in particular, is that it's symmetrical. So if you give it x and y, or y and x, you get the same value. And so as a result, the null distribution that you compute through a permutation test it doesn't care. It doesn't care in what direction you give, x versus y or y versus x. And because the observed distribution, the observed value also doesn't care. Then it doesn't really matter. Then you're going to get the same p-value in both directions. Is this a good thing? Well, I would say that let's discuss that in the next slide, maybe. But so going back a couple slides, we saw that the KL divergence is informative of how confident you should be. Maybe that's not a good characterization, but there's something about the KL divergence that is very closely related to test power, and ideally the optimal test would resemble the KL divergence, or at least intuitively this feels true. And so the natural question is, should we use an estimate of KL divergence as a test statistic? And this is not original. This has been done, right? So Vornovitsky has done this, and Kanamori before him. So, right, so we reformulate the test. So our question was, does P equal Q? And now we reformulate the question is like, well, is the KL divergence between P and Q equal to 0? Or is it greater than 0? This is mathematically equivalent to the previous one, but now the formulation is asymmetric. And why is that important? Well, is because your statistics will match your formulations, right? The way you generally come up with a statistic that is somehow an estimate of the formulation. So because KL is asymmetric in general, right, presumably an estimate of the KL will also be asymmetric. And so once you flip the two samples, you can end up with a different estimate, which gives you a different test statistic and a different p-value, which means you're now more confident in one direction than in the other direction, right? And since we're asking a symmetrical question, this sounds like a bad thing. It sounds like, well, we're asking a symmetrical question. Our answer should be the same, whether we ask it forwards or backwards, right? It's the same question. So is this a bad thing? Loaded question. So what if your samples are labeled in an asymmetrical way, right? What if you know that sample 1 is a simulation and sample 2 is observations? And what we're asking is this a believable simulation of the reality, right? That's not exactly a symmetrical question. These two samples really cannot be swapped without losing something. But this gets into very speculative territory, and I've done a little search of the literature to figure out how have people investigated this question, and I came up pretty empty, right? Can we utilize the label symmetry, or can we, as some kind of domain knowledge, to inform us in what direction we should use an asymmetrical test, and whether it's better to use an asymmetrical test than a symmetrical one, right? And some possibilities here are we may have a treatment group versus a control group, right? Or you may have simulations versus observations, like I just discussed. Or you may have a known instrument versus a new instrument that you haven't necessarily calibrated, and you're just unsure that the new instrument is producing accurate measurements, right? And then in which case the question becomes, is the new instrument good? Or does the new instrument need to be calibrated, right? That is not a symmetrical question. Right? So, which is the canonical one? So here's my opinion, really just an opinion. For the first question, treatment versus control group, I have no idea. And it probably depends on the problem, and maybe some empirical research, some meta science might shed some light on this, but I don't know. B, we're asking, does the simulation match reality, or is it a plausible? Does it look plausible given reality? Then I would say what we're trying to estimate is the KL of the simulated given the observed. But it's funny the way that this is written, but I want to say that KL from observed to simulated. And for question C, if we're asking, is the untested instrument good? Then we want the KL divergence from tested to untested. This is, again, only my opinion. And I would be delighted if people contradict me and with good arguments. So we haven't really been discussing how to do this in practice, and I made a little bit of progress over these years in some mathematical progress that may be helpful. And so I care. I forgot to say, but I really care about this being invariant to monotonic transformations. So that so ranked data is really what we're talking about. So if we rank all of the samples, right, that should be the sufficient statistic. That should be the minimal sufficient statistic for this problem, as far as I'm concerned. So, and what I discovered is that ranking the data leads to a nice universal distribution. Universal means that it's not dependent on P. So, yeah, so if the ranks are indeed minimally sufficient statistic, the minimal sufficient statistic, then we can losslessly bucketize the y's using the x's as boundaries, right? So essentially we're taking the rank statistic of each y relative to the x's, and we aggregate it, and we just call them counts. They become bucket counts. And what I've discovered, which is useful for testing procedure, is that under the null hypothesis, the vector of bucket counts follows a Dirichlet multinomial distribution. There's an event of P, and I have to thank Alex for really finishing the details on that insight. Basically, and the beginning of this, just go through the proof real quick. Or since the xi's follow P, that means that P of xi follows a uniform 0, 1. And this will also extend to the order statistics. So let x with the parentheses I be the ith order statistic, right? And for simplicity, we also define these extreme order statistics just to really make our lives easier. And we define the bucket lengths as the differences between these adjacent order statistics once scaled to the unit interval. What I discovered is that these bucket lengths, or the vector of bucket lengths, follows a Dirichlet distribution with parameter 1 everywhere, 1, 1 on 1 on 1. Which, by the way, is a generalization of the uniform distribution. Just like beta 1, 1 is the uniform distribution, Dirichlet 1, 1, 1 is uniform over the simplex. And then claim number 2 is that conditional on these bucket lengths, the vector of counts follows a multinomial distribution where the expected value is proportional to the length of each bucket, right? And then due to conjugacy, we end up with this nice, well, maybe not exactly conjugacy, but nevertheless, we end up with this result that the vector of counts, of bucket counts, follows the Dirichlet multinomial distribution. And we will be able to use that. So once we define our test statistic, we will be able to easily sample from the null in this way. So here's some discussion. Let's maybe move to the next. Yeah, I'll just skip to this slide. So towards a more structured H1. So what's the problem? So the problem is these bucket counts are treated as exchangeable, right? They don't account for the structure of the domain. The fact that first and second buckets are adjacent to each other should probably be relevant, right? So whatever statistic we define should probably take that into account. So as an intuition, if we have a few anomalously high counts, right, and this will happen a lot because when you have the Dirichlet 1, 1, 1, 1, you're going to end up with some really big buckets and then some really tiny buckets just by chance. And the big ones sometimes have really huge, really huge counts inside them. And you end up with this ambiguity of whether are these huge counts because the density ratio is large, or are they huge counts because the bucket is large, right? And this feels almost unresolvable, right? Almost unidentifiable. But I promise you, it is identifiable. Going back, when we have a few anomalously high counts adjacent to each other, that should be stronger evidence than if these high counts are far away. And that is not taken into account in the formulation that I presented. Right, so classical statistic does not really help. It doesn't know Occam's razor. You could try to do a spline-based model. This is the first thing I did. I made a stand model, fitting some splines, right? But it was a lot of work, and you're like, well, maybe should we use a more restricted alternative? Use smoother splines, maybe. Let me show you what I discovered. This is a very recent insight. This is as of yesterday. If you consider the order statistics for a uniform 0-1 distribution, the order statistics follow beta distributions. And so in particular, once we observe a given y in some bucket, what that means is that y is larger than some number of x's and smaller than the rest. So in particular, for the ith bucket, you're saying that I am larger than I minus 1 x's. Exactly. So you can plug that in, look up the formula for the order statistic of a uniform distribution formulated as a beta distribution. And this gives us an idea of how we can estimate the density ratio. We can now basically create this basis on the image on the top right. There's a basis of beta densities. And we can use some linear combination of these weighted by the bucket counts, right? So the first one here, if we see something in the first bucket, then we add one of these. Maybe we see 2 on the second bucket, then we add 2 of these guys. And at the end of that process, you have an estimate of the density ratio. I'm not claiming that it's a good estimate. I'm just saying it's an estimate. And it's going to have certain biases. But the good thing about our resampling-based methods is that they account for these biases, right? Because once you simulate from the null distribution, once you're doing the permutation test, you will it'll correct for those biases, at least as far as the significance testing is concerned. We don't have to get into the details here necessarily. Let's go back to the discussion of how to get more powerful tests. So yeah, how do you get more powerful tests? Well, increase the sample size. If you have money and time and grad students, and maybe human subjects, I don't know, it depends what you're studying. Or you can do better computing, and I mean this in a very broad sense. So I would say that, coming up with a better mathematical approximation counts as better computing, right? Or come up with better alternative hypotheses. So sometimes narrowing your alternative hypotheses might give you more powerful tests. But honestly, I don't remember exactly what this says. I'm a little confused on this point. And I would appreciate some expert advice or any advice on that question. Right, so generally speaking, narrowing your alternative hypothesis is a good idea. And so the reason for this is when we're talking about non-parametric testing, there's an illusion of precision, right? We have the impression that saying, oh, we're testing P equals Q versus P is not equal to Q. That leaves a lot of room for subjective preferences or priorities. Somebody might say, well, I really care about detecting scale deviations, or I really care about detecting heavy tails, or I really care about detecting the location change. And depending on what you prioritize, different tests may be more powerful. Right, so just to dispel any prejudices we might have had about this. Right, so that really becomes the question. The practitioner should ideally specify, what kinds of deviations, what kinds of alternatives they want to be sensitive to. Nevertheless, the notion of asymmetry, right, seems like it would be very useful in some cases. And yeah, I guess I just want to present one final slide. Oh yeah, this is the most important remaining slide, is that I don't know how much of this is prior work. Right, but I would love to get feedback from the community on that and hear some references. Great, and I would love to open up for questions. Alex?
Nothing's coming to mind.
Nothing's coming to mind? Okay. Anything unclear?
No, that all made sense.
Okay.
Let's see. Yeah, I don't
know. So I can present this other slide that was lower priority, I guess.
Sure.
If we're talking about binary data, we may want to consider this asymmetrical test. So there's a different idea. So this is not using KL divergence. This is merely using the idea that essentially hierarchical modeling as as one possible way to do this kind of testing. So basically what we're saying is that if X is canonical, then we may model our data as being binomial with sample size n and some probability, using a slightly non-standard parameterization here. You just log transform, that's all. And then Y is also binomial, but then the probability for Y is derived from the probability of the other one. So let's say
I
Q.
think you mean plus epsilon, not plus log epsilon. Oh no, where plus log epsilon is normally distributed. Never mind. Yeah, that's fine.
Yeah. So just basically like a log normal, using a log normal multiplier, right? And maybe logit is better. That's not the point here. The point here is that you can reformulate things in an asymmetrical way, right? We're now asking the question, is sigma equal to 0? Right, so sigma is the standard deviation of this noise term. And we only get one observation, but it is sufficient to identify it. And then the null hypothesis is sigma equal to 0. Or not, right? And then you can consider the backwards version of this, in which Y is the canonical sample, and the probability for X is derived from the probability of Y to this model, and then you ask this, is tau equal to 0? I believe these will give you different p-values, in most cases. Does it agree with the KL divergence, right? In the same, these questions are not entirely settled because I haven't fully implemented everything. But it seems intuitively like this first model here is one that'll do better if X is the canonical sample and Y is derived from that. There is a danger in some of these models of your implementation potentially introducing asymmetries, right? Like when you're using a spline model for density ratios, you might be unwittingly privileging the KL divergence in one direction versus the other. So I feel like maybe using splines to model the log density ratio resolves this issue, right? Because generally splines will be, at least numerically speaking, right, they're symmetric around 0. So yeah, so just something to watch out for. But I feel like this is like I'm very close to making some simulations that at least showcase the performance of these tests and how they compare to other tests. Yeah. Did you think of any questions in the meantime, Alex? It's okay. Cool. Well, thank you. Are you still there?
Yep.
Okay. Okay. Thank you. Thanks, Alex.
Mhm.
Okay.
Okay.
Right. Let me the recording.